Okay, be honest. When you hear thermodynamics, do you think fun? I don't. It's one of those sciencey things that feels like a total brain drain.
I can see that.
But today we're going to prove it's actually like really cool.
It is really cool.
And more importantly, it's super relevant to your life, everyday life.
Absolutely. We're talking the energy and everything, like the food you eat.
Yeah.
How your car moves.
Right.
Even this crazy weather.
Seriously.
It's been nuts.
So you sent in this blog post called Thermodynamica, Importancia y Leyes, which I think translates to thermodynamics, importance and laws.
Exactly.
So clearly you're ready to dive deep.
I am.
It's from a website for chemical engineers. It's originally in Spanish. But don't worry, we've got the translation covered. And our expert is here to make sure it all makes sense.
Absolutely.
No need to be fluent in Spanish for this deep dive.
No.
So this blog post starts by throwing it way back to the Industrial Revolution, which might seem kind of random.
Yeah.
But it's actually a clever way to show how we understand energy.
I see.
How it's evolved.
Exactly.
It's the Industrial Revolution was all about energy and machines.
New technology, yeah.
And tech, it was a total turning point, right?
Big time.
And understanding energy was to make all that happen, crucial.
Absolutely, yeah.
It's wild, right? Even something like energy,
Mm-hmm.
it has this whole historical backstory.
Totally. Science, it's woven into history.
Totally. So the blog post talks about three main types of energy: potential, kinetic, and chemical.
Okay.
Can you give us some real world examples?
Sure.
So it's not just words on a page.
Yeah. Of course. Imagine you're about to bungee jump.
Okay.
Standing at the top, all strapped in, you're full of potential energy.
Okay.
Right. That's energy just due to your position.
I see.
Then you jump.
Yeah.
And as you're falling, that potential energy is turning into kinetic energy, the energy of motion. And finally, think about the food you ate that morning that gave you the energy to jump.
Right.
That's chemical energy stored in the bonds of those food molecules.
So we've got the energy basics. Now, the blog post defines thermodynamics as the study of energy in all its forms, not just in machines.
Right. It's a much broader lens than you might initially think.
Okay.
And for chemical engineers, the folks reading this blog, it's crucial for understanding things like heat transfer, pressure, temperature, volume.
Gotcha.
They often use these cylinder piston systems as visuals to help explain those concepts.
Speaking of visuals, the article uses this line, it's very dramatic, about harnessing the powers and forces of nature.
Ooh.
It sounds very movie trailer-y.
Yeah.
But it actually highlights the practical stuff, right?
Exactly.
Applications of this.
Thermodynamics is how we create products, get energy from raw materials, design better processes, more efficient processes.
It's the science behind so much of what we rely on, every day.
You don't know what you got till it's gone, right?
Right. Exactly. We take it for granted, but without it. Whoa.
A very different world.
Okay. Ready to tackle the laws?
Hit me.
First up, the first law of thermodynamics, the conservation of energy.
Right. This basically says energy cannot be created or destroyed,
Hold on.
only transformed from one form to another.
So it's like energy Tetris, kind of?
It is energy Tetris.
You can't make new pieces appear or disappear.
Right.
They just change shape.
Exactly.
So when you burn fuel,
okay,
the chemical energy in the fuel is converted to heat and light. But the total energy, the amount, stays the same.
Right.
It's just changing forms.
Exactly. And the blog post even gives you a simple equation for this.
Oh, okay.
EUUQW.
I'm already lost.
Don't worry about it.
Okay.
Don't let the symbol scare you. It just means the change in internal energy, that's the delta U, of a system is equal to the heat added to the system, that's Q, minus the work done by the system.
Got it. So there you go.
Okay. On to the second law, where things get a little messy.
Yeah.
Right.
A little messy.
This is where we get into entropy.
Entropy.
Right.
Which is basically a measure of disorder, randomness.
Okay.
It states that the total entropy of a system always increases over time.
So my inbox after vacation, no matter how organized I try to be, it's just chaos.
Yeah, exactly. Or think about a pristine sandcastle on the beach.
Yeah.
Eventually the wind, the waves, it'll erode. It'll just become part of the sand.
Right.
That's entropy.
And this law also explains why time travel is likely impossible, right? Because you can't reverse that increase in entropy. Once it's disordered, you can't go back.
Yeah, the arrow of time only points forward, right.
The blog post even mentions a scientist named Sadi Carnot, who figured out that perpetual motion machines are impossible because of this law.
Yeah.
That's kind of mind-blowing when you think about it.
Yeah.
It is. It is. Carnot's work was groundbreaking. He showed that no machine can operate at like 100% efficiency because some energy is always lost, like as heat, because of this whole entropy thing. That loss of useful energy, you can't avoid it.
So the second law is basically like you can't win, you can't even break even. There's always going to be some loss.
That's a good way to put it.
The blog post gives an equation too.
Yeah.
DSDT, O00, meaning entropy never decreases in an isolated system.
Right. The change in entropy ds over time ADT is always greater than or equal to 0.
All right. We've covered the two main laws. Now the blog post mentions two kind of bonus laws.
Yeah.
The 0th and the 3rd.
Okay. Yeah, these are more about refining our understanding of thermal equilibrium and the limits of entropy.
So it's like the director's cut version of thermodynamics.
Exactly. The 0th law might sound confusing.
Yeah.
But it's pretty simple. It just defines thermal equilibrium.
Okay.
Imagine a hot cup of coffee
Mm-hmm.
and a cold glass of water. You leave them on the counter, eventually they reach the same temperature. That's thermal equilibrium.
Got it.
And the 0th law says if two systems are each in thermal equilibrium with a third system, then they're in equilibrium with each other.
So it's like a cosmic game of temperature tag.
You could say that. Now, the 3rd law is a bit more complex. It says that as the temperature of a system approaches absolute 0,
Absolute 0.
which is the coldest possible temperature, the entropy of the system also approaches a minimum value.
So basically at absolute 0, things completely freeze, molecular motion stops, and entropy is like at its lowest point.
That's a great way to put it. It's like the universe hitting the pause button on disorder.
That's incredible. And to really grasp these laws, I encourage you to check out the full blog post.
Yeah, definitely.
It's like a gold mine of information just waiting to be explored.
Don't just take our word for it. Dive into that source material and see what you can learn.
Okay, we've covered a lot here, but before we move on, I have a question for you.
Okay.
If entropy always increases, does that mean the universe is destined to become completely disordered? Or are there forces out there working against that trend? It's something to think about
That's a big question.
as we continue our deep dive.
It is.
That's a question that could keep us up all night.
for sure.
But for now, let's bring it back down to earth
Okay.
and look at how the blog post connects these laws to chemical engineering.
Right. So it really emphasizes how these principles allow engineers to design and optimize all sorts of processes, from creating materials to developing energy sources.
It's like they have a master tool set,
It is, yeah.
like manipulate energy and matter.
Precisely. The article really stresses how important it is for chemical engineers to be able to predict the properties of substances, mixtures, think about it, right? To design a chemical reaction or create new materials.
Yeah.
Or just make sure that an industrial process is safe.
Right.
You need to understand how energy interacts with matter.
It's easy to forget, like all the science behind
Yeah.
the simplest things.
Absolutely. We take for granted the complexity behind so many products. Like every time you pick up your smartphone, you drive your car, or even when you just take a sip of water,
Wow.
you're interacting with the results of thermodynamics.
It really is mind-blowing when you think about it that way.
Yeah.
Now let's look at some specific examples the post mentions.
Okay.
One that really stood out to me was the discussion of power plants.
Oh, yeah. Power plants are a classic example.
There's such a good example of how we convert energy from one form to another, right?
It's beautiful, really.
Guided by these fundamental laws.
Mm-hmm.
It's amazing how we can take coal, oil, even nuclear energy and turn it into electricity.
Yeah.
It powers entire cities.
Yeah. And the efficiency of those conversions
Yeah.
is a constant challenge.
For engineers.
For engineers, they're always trying to minimize energy loss, right? Maximize output, squeeze every bit of usable energy from the source. That's where a deep understanding of thermodynamics is really key.
Right.
Helps them design and optimize these systems.
The blog post also mentions how these principles apply to renewables,
Mm-hmm.
solar, wind power.
Right.
That feels especially relevant these days.
Absolutely. Even though the sources of energy are different,
Yeah.
the underlying science is the same.
Right.
Whether you're talking about sunlight, wind, geothermal, it's all about capturing that energy, converting it to a usable form, and minimizing losses.
So fossil fuels, nuclear renewables.
Yeah.
Thermodynamics gives us this framework, right?
Yes.
To use any energy source well.
Exactly. And as we deal with things like climate change
Right.
and the need for sustainable energy,
Yeah.
understanding these principles is going to be even more important.
Yeah, you really start to realize that thermodynamics isn't just this abstract thing.
It's not, no.
It's at the core of how we're dealing with some of the biggest issues facing humanity.
It really is. The more we understand and can use these principles, the better we can create a sustainable and energy-efficient future.
Okay, so we've talked power plants, renewable energy.
Mhm.
The blog post mentioned a couple other things too.
Okay.
One is refrigeration.
Refrigeration, another great example of how we can manipulate heat transfer,
Yeah.
right?
Yeah.
To get a specific result.
Keep things cold.
Exactly, keeping things cold. It uses these thermodynamic principles to move heat away from a space
Right.
and make it cool inside.
So it's not like we're creating cold, we're just moving heat around.
Got it. It's all about managing that flow of energy.
Yeah.
And believe it or not, those same principles that are working in your fridge,
Yeah.
they're also at work in the human body.
Whoa. So it's not just machines, it's literally the science of life itself.
It is. Every biological process,
Hmm.
digestion, muscle movement, it all involves energy transformations. And those are governed by thermodynamics.
It's incredible, like the interconnectedness of it all.
It is.
This deep dive has been amazing.
It has.
And I feel like we've only just scratched the surface.
Oh, we have. But we've laid a good foundation, I think.
Yeah.
And remember, that blog post is there for you. It's got even more information
Yeah.
to help you understand thermodynamics and really see how it works in the real world.
It's like we've given you the keys to this treasure chest of knowledge,
There you go.
and now it's up to you to unlock it.
Yeah,
It really makes you think, like how much we depend on this stuff,
it does.
and we don't even realize it, you know?
It really highlights how crucial thermodynamics is, to just understanding the world.
Yeah.
And it shows that there's always more to learn. Always.
Exactly. And speaking of learning, we keep talking about this blog post.
Rightly so.
For good reason.
Mm-hmm.
If you want to go deep, like really deep into thermodynamics,
Mm-hmm.
this is where you start.
Absolutely. It's got those clear explanations, real world examples,
Yeah.
even questions that make you think. It all helps you get it.
It's like a launch pad.
Yeah.
We've given you that initial spark, hopefully.
Little spark.
And the blog post is the fuel to keep the fire going.
Love that.
Who knows? Maybe this deep dive will inspire you to explore even more, like into science and engineering.
I hope so.
It's a whole world out there full of possibilities.
Absolutely endless.
So remember, understanding thermodynamics, this isn't just about memorizing equations or passing a test.
No.
It's about getting it, like how energy shapes our world.
Yeah.
From tiny cells to the whole universe.
It's about seeing the connections, the forces at play, and then using what you learn to solve problems, build new tech, make good choices about the future.
So we're going to wrap things up here.
Okay.
But definitely go check out that blog post. It's full of good stuff.
Yeah.
And it'll help you on your journey into the wild world of thermodynamics.
It's been great exploring these ideas with you.
Likewise.
And hopefully you've got a new appreciation for how powerful and relevant thermodynamics is.
Thanks for joining us on this deep dive, and keep that curiosity burning.